a lot of people in this town know me, but I'll just introduce myself. My name is Mike Thompson. Been involved in ASIC and FPGA verification, mostly here in Ottawa for about 25 years. I'm actually not really sure when I started doing this as a mainline thing. Predominantly ASICs, and that's going to be, that when I talk about this kind of work, I'm talking about ASICs and SoCs as opposed to FPGAs. But almost everything I'm talking about here can be, if you're involved in FPGA work, can be transposed onto that. I'm going to be a little bit coy. I'm going to back up a little bit. I know we're talking about RISC-V and RISC-V integration into SoCs and RISC-V as is open source hardware IP. But I'm going to back it up a little bit to just talk about open source hardware IP in general, and then we'll go forward down into RISC-V. Before I start, I should define what the heck I mean by hardware IP. So this is it, hardware intellectual property. We're done. That's not a really good explanation of what I mean. What I really mean is a synthesizable description of a digital functional block or a digital functional unit. Typically people will call this, typically this is implemented as RTL, and typically people will just call it the RTL or the IP. So if, whatever term you want to use it, that's what we're doing. There are lots of other kinds of hardware intellectual property available. You can get hard macros, for example. A lot of FPGAs have IP right on the die, whether you use them or not. I'm not talking about those. I'm talking about synthesizable descriptions of functional blocks. These typically come with well-defined user interfaces, so ports on them that use things like AMBA bus or AXI Stream or something like that. Typically they define some well-encapsulatable function like a PCI Express endpoint, a DRAM controller, or hey, look at that, an embedded microprocessor, just as an example. Okay. So why do we use this stuff? Why? This is very pervasive in industry. Why the heck do we do this? And in industry, it's all about reducing costs, right? The reason we use IP at all, and the reason we use hardware IP is to reduce our costs. And we can reduce costs right across the board, right from physical implementation all the way up to documentation and back again. It's important to understand that none of these costs can be eliminated by using IP. It can all be reduced drastically. Verification is one of these areas that is a little bit thorny. It's hard to really get rid of all your verification costs using IP. A big problem is just assessing the quality of the IP. How do I trust this stuff? How do I know that I don't have to verify it again? And we still have to verify the usage. And this is a critical point that a lot of teams stumbled over in the early years. If I'm going to put your IP in my SoC, I have to make sure that I'm using it in a way that you intended, not in a way that I want it to work. So how do I make sure that I do that? Okay, so I want to talk a little bit about how hardware IP is used today in industry. This is a well-established process. This is not what it was like 20 years ago. 20 years ago, we used to call IP other people's problems. And so when we would pay money to buy other people's problems and put them into our chips, we don't call it that anymore. We just call it the IP that we bought from some established vendor, Cadence, Synopsys. There's lots of people, lots of organizations selling high quality IP. So over many years and a lot of stumbling and hard learning, the ASIC and FPGA development community has learned to trust open source, or not open source, has learned to trust hardware IP. One of the things that came into this is to understand that it reduces your effort, but it doesn't eliminate your effort, particularly on verification. I'm going to keep pounding on verification through this talk. Part of what has gone on here is that the people selling the IP have learned of the importance of supporting the people that are buying the IP. It's not just a question of dumping it on people and taking the money and leaving. You become a partner with somebody when you give them some of your hardware IP. You need to provide quality documentation. The RTL is not the documentation, no matter what anybody tells you. On-site engineers, quite often, if you are buying IP from a third party, they will provide engineers that actually will work with you on site to help you integrate their IP into your SOC. And this is one of the ways that we get around this usage problem. Strict control of the implementation. This is something that's going to come up again in my talk. This is typically closed source IP. It's sold to you as a black box. You can't actually see the RTL. It might be encrypted. There might be other protection schemes on it. And the vendor has strict control over this. They do this for two reasons. Number one, they don't want you to run away with their secret sauce. Number two, they want to have strict traceability. This is an important thing, and I'm going to come up to this. They know which versions have which issues, which versions work in which process technology, which versions have been verified with which regression suite, which bugs have been fixed and where. That's important information for you as IP users. How about open source hardware IP? How well is that used? We want to use this again to reduce costs. Industry really only cares about one thing. It's the money, honey. Reduce costs. That's really the only thing that people in industry seem to care about. We want to take advantage of an ecosystem. This is another way that we reduce costs. The great thing about open source IP is it tends to create an ecosystem around it. There tends to be people coming out of university that already know about this IP. This is really true for RISC-V and will become more true in the future. People come out of university already knowing about RISC-V because they did something with RISC-V in their graduate work. There are a bunch of hardware and software tools that will naturally get developed. We're actually going to get a chance to play with some of them right now today. So this is the kind of thing this is the ecosystem that SOC developers want to take advantage of. Another thing that differentiates open source hardware IP from closed source IP is the ability to make user modifications. I'm going to talk a bit about that as well. This is unique to open source and I think is a bit of a game changer. Last but not least, you use open source because you have a desire to contribute to the open source community. And I'm going to be very blunt about this. Industrial users don't care so much about that. They really don't. This is something that, as people that work in their basement we care about, or people working in a university care about, or in academia. Industrial users want to get this IP, use it to make money. Okay, so just how much use does open source IP get in industry? And I've talked a bit about how much open source IP gets used, or closed source IP gets used in hardware. A lot. I don't think there's a single SoC that I've worked on in the last 15 years that hasn't used IP from somebody. Open source hardware IP is not well established. This is in contrast to open source software, which is well established in industry. There's a bunch of barriers to adoption for this. One is there's a perceived lack of quality documentation that comes with open source IP. I believe this is a perception, but perceptions become reality. So that's something that has to be dealt with. There is a lack of direct vendor support. Open source IP, generally speaking, doesn't have an army of application engineers that come and visit you at your site to help you integrate the IP. This is a problem because this is something that is pervasive in industry today, something that people expect. So this is something that the open source hardware IP community needs to address. And perceived low quality verification. I'm a verification engineer. I'm going to say a couple of controversial things about the verification of open source hardware IP in a few slides here. This perceived low quality is a big problem. So I want to step back a little bit. I want to talk a bit about verification hardware verification in general, so pre-silicon verification of RTL. Just to sort of give us a little bit of a context here. So now I'm not talking so much about open source IP. I'm just talking about the problem of verification. As my boss has told me, it's helpful to think of these things as challenges, not problems, Mike. Anytime it's a challenge, it's a good thing, right? There's really 4 things that have basically allowed me to put 2 children through university, and here they are. Every design has functional defects or bugs. Every one of them. It's impossible to know where they are before you start working on it. This is a real big problem. I've had a boss come to me and say, how many bugs are you going to find and what blocks are you going to find them in? Well, I don't know. There's no known method of demonstrating where these bugs are, right? Or that you found all the bugs. There's no way to know. You can't say to your boss, yeah, I found all the bugs, we can tape this out. You just cannot make that statement, right? And last but not least, it costs much more to find and fix bugs than it does to create them in the first place. Currently in industry, building an SOC is starting to cost an awful lot of money. The first build is very expensive. And this is adding pressure to development teams to get it right the first time. So this pressure to get it right the first time comes from two things that are a result of modern semiconductor process technology. The first is schedule impact. If you have a defect in silicon, respinning that silicon to get rid of the defect is going to cost you weeks or months, probably months. That's time that you don't have to spend. The other is dollars. The cost to spin an ASIC is extreme. It can be $1 million and up. This is the verification problem in a nutshell. You've got a bunch of things that you just don't know and can never know, yet you've got all this extreme pressure on cost and time. A little bit, I'm just going to talk very quickly about the cost of bugs. You've probably seen a chart like this multiple times, and what we're trying to say here is, as we go through the life cycle of our software, the cost of fixing a defect goes up, right? Well, we've got a similar curve in hardware. The problem is that the absolute numbers are much larger, right? The absolute cost of fixing a bug in hardware just goes up and up and up. This life cycle cost in software is saying that when you're in production, it's going to cost you 30 times more than if you fix the bug at the requirement stage. Well, it's at least an order of magnitude more expensive to do that in hardware. So all of this drives the state of the verification industry today. We have no known method to find bugs. Anybody tells you that they have a method to find all the bugs in your design is either not aware or lying to you. One of those two things, right? I will never tell you that I found all the bugs in your design, never. I will tell you something like, I found all the bugs I'm going to find, but I've never found them all, right? Because of this, we use a lot of different techniques. Simulation is still the most popular. Emulation is growing in popularity. FPGA prototyping, formal methods, code reviews. People pull their hair out trying to find another way to verify RTL designs before they go into silicon. One of the things that's very popular and something that's very big with me is using qualitative measurements of verification completeness. This is typically called coverage, and there's lots of different techniques here. Compliance test plans, where you just have a laundry list of features that your device must support, and you just say, yes, I tested that, yes, I tested the next one, so on and so forth, until you've tested them all. Code coverage is very, very popular, and a thing that's big with me is functional coverage. So these are the kinds of things that we use to measure completeness, understanding, of course, that we can never get to 100%. Okay, so let's bring this all back to open source hardware. I've just talked about some of the challenges in verification of just, RTL verification in general. I want to talk about open source hardware specific challenges, right? I like to compare and contrast things all the time as an aid to understanding. So I'm going to talk a little bit about the distinction between open source hardware and open source software. Open source software is really popular. There's lots of it out there. I developed this presentation using open source software. Works just great. I love it. I think there are two reasons that I sort of gravitate to explain why open source software is so popular, so pervasive, so widely used. One of them is the cost of finding defects is spread across a huge developer base, right? How many eyeballs have looked at the source code for GCC? Like literally thousands times 2, right? Lots of people looking at this code, right? The cost of fixing a defect is acceptable, still high. The software lifecycle curve still applies, but punching out a new release costs tens to hundreds of thousands of dollars, as opposed to silicon, where it's much more expensive. So these two things add up into what we have today, which is a very large, very diverse, very high quality set of open source software that we all benefit from using. Right. Let's contrast that with open source hardware. Much smaller developer base. For every hardware developer out there, there's 100 or more software developers. There's just fewer people developing hardware, right? Much higher cost to fix bugs. If you have a bug in silicon, you have a problem because it's going to cost you real money to fix it. So that adds up to a smaller set of lower quality open source hardware IP. So there are differences between hardware and software that are real and important to understand. And one of the reasons we don't see a bunch of high quality open source hardware IP is because there's just fewer people doing it, and it costs a lot of money to fix the bugs when people do the work. Okay, so just a little in a nutshell about verification, and then we'll swing back to open source IP. Verification is not a solved problem. Anybody that tells you verification is a solved problem it really doesn't understand the problem. Anybody who's pushing a new technology has to take this seriously. In this room, I think we're all interested in pushing the idea of open source hardware IP. We need to take verification of that IP very seriously. We need to have a first time right mindset. That doesn't mean that all the bugs will be eliminated, but that means anytime we go to silicon, it has to be good enough to go to production. It can't be just something that gets punched out and we'll see what it does in the lab. It has to work the first time. We have to have confidence that it's going to work the first time. Right? The open source hardware IP has to support things that address its unique capabilities. We need to provide quality documentation, some sort of support model, right? The hardware IP vendors of the world have a good support model. Open source hardware IP is going to need a good support model. Industrial grade verification completion metrics. This is really big to me. And I think it's really big to the people that would use open source IP. They can't just see a checklist and say it's done. They want to be able to see something that proves that you've done a good job with verification. And last but not least, a method for users to re-verify any IP that they may have modified. Okay, so are we there yet? Do we have something that satisfies all of that? The RISC-V community already has a large set of cores available. Rick showed probably what is probably an incomplete list, but it was a large list of cores that are available. You've each got on your desk hardware instances of a RISC-V core, right? So we must be done, right? We've already got a bunch of cores in silicon, and several industrial users have their own implementation of RISC-V core ready to go. So we must be done, right? Well, I'm well known for making bold and controversial statements, and this is my bold and controversial statement for this presentation, right? As far as I'm aware, none of the RISC-V cores available to the open source community are fully verified and production ready, and that includes what's on your desk today, right? What you have that's on your desk today will work, and it's great for learning about RISC-V, but if you go to production with this thing, unless you put an awful lot of software warts on top of it to hide all the hardware bugs, you're going to have a hard time going to production. The RISC-V core in particular has known bugs. You can go to GitHub and look at it. Issue 132 is the one that I know. The thing that I think that should concern us the most is that the completeness of the verification effort for any of these cores is not known. If anybody knows of some completion metrics for any RISC-V core, please come and see me, because I've looked. I can't find it. I know that people have done some tests. I know that people have filed some issues in GitHub. I know that some of these issues have been fixed, but I don't know. I can't find any information on how complete any of these verification efforts on any RISC-V cores have been. this last little bullet here, the risky bug that I'm talking about is not attributable to any specific version of risky. Right? I actually contacted the people that found this bug and say, what version did you find it on? And they said, oh, I don't know. I just about died. You don't know. Has it been fixed? Well, I'm not sure either. What version would it be fixed in? Well, the latest, I guess. If open source hardware IP is going to be taken seriously, we can't have conversations like that. Okay, so how do we get from where we are now to where we need to be, right? So this is where I get a little bit coy because, of course, some of this stuff is stuff that Rick has already talked about. Some of this stuff is what the Open Hardware Group is interested in doing. I'm obviously interested in this or I wouldn't be here today. So, part of what I'm talking about is part of what is already going on, right? So start with a minimal set, right? The Open Hardware Group is talking about starting with the risky core and the Adrian core. There's a lot of RISC-V cores out there. Don't start with them all. Find a couple that really matter to you, right? Execute complete verification cycle on these things. I'll talk about what that is in just a little bit. Fix the bugs, make the updates, get a proper repository in place, make it available to the community, right? Develop some verification environments. A verification environment is that's a fancy word for a bunch of test benches, right? Develop these verification environments with both industry and open source communities in mind, right? Use industrial grade tools, right? This is a bit of a controversial topic for some, but for me, industry's not going to take open source hardware IP seriously unless they can apply the tools that they use every day on their stuff. That means proprietary tools, right? Ensure all of the code that you develop is open source, just like the core itself is open source. So this is called VIP or verification IP. So any code that you develop for your verification environment should itself be open source, right? And your verification environment should have specific emphasis on the thing that makes open source IP so exciting, which is supporting user modification of the open source code, right? I mentioned this as a specific bullet. A previous version of my slide didn't have this until I talked to the people that found that risky bug. So I added this bullet. Strict configuration management and revision control has to be applied. So that's how we get from where we are now to there. I'm going to talk a little bit about the beginnings of something like that, right? So RISC-V open source simulation environment. There's a bunch of organizations working, they've been working together over the last several months to basically start putting some of this together. I have not been actively involved in this, but I've been watching it from a distance, and this is the germ of the effort that is going to get us from where we are today to where we need to get to, right? So we need a verification environment written in System Verilog that uses the universal verification methodology. I can stand here all day and argue why you should be using these verification tools, why you should use these languages. The big answer is that's what industry is using. That's what the people who build chips to make money expect you to use. That's what everybody's using. I could give you a whole bunch of other arguments that are even better than that, but really it boils down to that. Let's use some modern verification techniques. In simulation, one of the best ones is constrained random generation. There is an instruction stream generator by Google that is written in System Verilog using the UVM that is available now. So that's a good starting point. If you want to know more about this, and everyone gets excited about this because it's got the Google name on it, just cut and paste RISC-V processor verification platform into your Google search bar. You'll find out way more information than you want about it, and one of those links will actually point you to the source code on GitHub. We'll need an instruction set simulator as a reference model. There's a company called Imperis that has made one of these available. It's written in C, it's open source. Last but not least, you need checking and functional coverage. This should also be written in System Verilog. If you did all that, you'd have something that looks a little bit like this. This is in place today, right? You've got over there on the, will be your far left, is the Google random instruction stream generator that generates RISC-V instructions and presents them both to this guy right here. This is our open source hardware IP. It's the RTL model. Guys like me tend to call it the device under test. Down below it is the Imperius instruction set simulator. They both get the same instruction stream. They both hopefully produce the same results. We compare those results. If they're wrong, we either have to find a problem in the test bench, in the instruction set simulator, in the RTL, or maybe all three of those. And we just keep doing that until we've done all the testing. What's not shown here is the functional coverage that gives us an indication that we're getting close to done. I'm going to talk a little bit about this, mostly because there seems to be a lot of interest in this. It's also a bit of an advertisement for modern verification techniques. This thing has got the Google word attached to it, so everyone's excited about that. I'm going to back up a bit and talk about constrained random generation. The instruction stream generator from Google is a constrained random generation component. The reason these things got going in verification, probably about 15 or more years ago, is when this was a new technique, is because people were writing these huge libraries of test cases and getting bogged down with maintenance. It was just killing them. Anytime you made a small change in the RTL, you had to change about 300 test cases. It was killing us, right? Current practice is to basically define your stimulus as a small set of constraints, hopefully small set of constraints, and let the tools do the work of generating the stimulus for you. A small change in the RTL results in a small change in the constraints, and there's just less effort to maintain your design. This is well supported. There's a bunch of proprietary tools that support this. It's also supported by System Verilog, System C. Using constrained random to generate instructions for a processor is not a new idea. People have been coming to me over the last 2 months going, Google's got this constrained random generator for instructions, and they're all excited because this is the first time they've heard about it. I just want to calm everybody down. This is not risky technology. I made a joke. I didn't intend to. Right. This has been done for a while. Those are four papers. The last one actually is a Google presentation given last year at the RISC-V Summit. You can download the code from that URL. So this is a well-worn path. It's the right path to take, but it's not a really fancy path. I don't have time to go through this. Constrained random generation 101. This stuff's real, right? You define your transaction as a class. You define your constraints as a class, and this thing will generate instructions. I don't know if you can see this. It's a bit of an eye test, right? You can generate loads, or stores, or shifts, or arithmetics. Basically define what are the things that you want and let the tool do it for you. There's other verification environments, and these are very important. We cannot have just simulation. It's important to do others. Formal sign-off is a very, very important thing. Formal verification is rules-based. You basically define what the RTL does or should not ever do, and you mathematically prove that the RTL is compliant with that. Prototyping is big, particularly for something like a processor core, because you want to run software and you just can't run software in a simulation environment. Okay, so I wanted to bring this back to the tools. Everything on that test bench slide I showed you is implemented as open source code, right? So the code is open source using non-proprietary languages, but the tools that run them are proprietary tools, right? We're currently running this test bench on the Metrics System Verilog simulator. The Imperius tool is itself proprietary, but this is the kind of thing that the folks in industry expect to use. People expect to use tools from EDA companies. They expect to pay money for them, but we want to make sure that the code that they're running can run on any of these platforms. Lots of work remaining. We have that prototype test bench, but I don't want people to think that we're done yet, right? We need to basically get things like a real compliance test suite. I know that the RISC-V Foundation is working on that. We've got to actually implement that as a in simulation. We got to integrate all these components in that test bench into an end-to-end verification flow. We need to prototype a flow to support user extensions. This is really important. And documentation. This is really super, super important. If we can do all of these things, then I think that we've basically shown people how to use open source hardware IP. All right, wrapping it up. I believe open source hardware IP is an idea whose time has come. People have not been paying attention to it for a long time because of some of the things that I mentioned, but I think that's going to change. For us to be successful, we need to address the concerns of the industrial users. People just aren't going to take this seriously if it's a bunch of kids working in their basement, right? The two things that industrial users of IP care about, cost and quality. After that, it's all yeah. The unique capabilities of open source hardware IP could be game changing. I'm really excited about this, right? You get access to this community and you have the ability to produce your own variant, to add your own secret sauce. This, I think, is unique to open source hardware IP. This is why I'm really excited to be part of this. Thank you.